Okay, in this presentation we are going to look at a uniform probability distribution example. So this relates to the dimensions of a cube. Now essentially the thing about a cube is that the measurements in the height, breadth and width direction are the exact same. Okay, so the equal measurements in each of the three dimensions. So the length of a side of a cube is chosen at random from the uniform distribution on the interval 2 and 8. So the minimum value is 2 and the maximum value is 8. Okay, calculate the following. Calculate the probability that the length of the side is between 4 and 6. Calculate the probability that the volume of the cube is between 27 and 216. And calculate the expected volume of the cube. Okay. So this is what we're told. The length of a cube is the length of the side of the cube, x, is chosen from a uniform distribution on the interval 2 to 8. This means x is a random variable that is uniformly distributed with a minimum of 2, so a equal to 2 and b equal to 8, where b is the maximum value on the interval. Okay, it's the upper bound on the interval, you may say. Anyway, so exercise A, the probability that the length of the side is between 4 and 6. So let's look at the probability density function here, the PDF. Now for a uniform distribution, it is constant over the interval. So we have an expression here which is 1 divided by b minus a. So here a equals 2 and b equals 6. So we have f of x equals 1 divided by 8 minus 2, which is 1 over 6. And it's as simple as that. We have a constant term, essentially 1 over 6. So that's straightforward enough. Okay. So I'll revert back to that constant term later on when we're evaluating other integrals. Okay, so the probability that x is between 4 and 6 is as follows. Probability of 4 less than or equal to x less than or equal to 6 is evaluate the interval from 4 to 6, f of x dx. This is probably a little bit overcomplicating things, to be honest with you, but we'll just sort of stick to the same system each time for each probability distribution. In this case, it's straightforward enough, but in other cases it'll be a bit more complex. But however, you use the same system each time. Okay, so our integral for this interval between 4 and 6 is the definite integral between 4 and 6 of 1 over 6 dx. Okay, so that's essentially a constant term, and we have the definite integral when we have essentially the integral of 1 is 6 minus 4. Okay, so x, when we integrate 1, we just get x, and we evaluate it between the upper and lower bound. We have 6 and 4. 6 minus 4 is 2. So essentially our answer works out to be 2 over 6. Essentially that middle component there is a definite integral. It's just very straightforward, and so much so that you almost sort of might miss it. But anyway, definite integral. So anyway, therefore our answer is 1 over 3, which is something you probably might be able to sort of figure out directly. But as I sort of said before, it's probably best that you actually take the same approach each time, particularly as you just get used to the process when you deal with more complicated probability distributions. Okay, moving on to the next one. So they're a little bit more complicated here, so we have to sort of evolve a bit of our thinking. The probability that the volume of the cube is between 27 and 216. So the volume of the cube, v, is given by v equals x cubed. Okay, so to find the probability that 27 is less than or equal to v less than or equal to 216, which is to say the volume is between 27 and 216, we need to find the corresponding interval for x. So that's straightforward enough, really. So essentially what we're asked for is the probability that x cubed is between 27 and 216, which is the equivalent of taking the cube roots of each side, which is asking what is the probability that x is between 4 and 6. Okay, so we're taking the same approach again. We're just doing a definite integral again. That is the integral between 3 and 6. So 1 over 6 times 6 minus 3, which is 1 over 6 times 3, which is 0.5. That's it, essentially. So the probability that the volume of the cube is between 27 and 216 is 0.5. Okay. So exercise B is straightforward enough, really. Essentially, the crucial thing is just remembering, essentially, the rules of a cube and what it is, essentially, how that relates to the side. And once you sort of recall that bit, really, you're good to go. And just a sort of important thing to say is that you can sort of make these sort of sequential steps from the first bullet point to the second bullet point to the third bullet point. That is part of the intuition of the question, so it's a valid approach. Okay, so moving on to exercise C, we're looking at the expected volume of the cube. So this is given as follows. We recall that V is the volume, and the expected value of the volume is the expected value of x cubed. Now, just recall, suppose gx is a generic function of x, and the expected value of gx is as follows. The expected value of g of x equals the integral of gx times f of x dx. Okay, gx could be x, x cubed, x squared, square root of x, and so on. So g just means generic. It's a placeholder for all of the possible types of functions in x. So for this example, for a uniform distribution where x is a uniform random variable on the interval 2 to 8, the expected value of g of x is, the integral from 2 to 8 of g of x divided by 6 dx. Okay, you can take that constant term out, essentially. Just as a quick remark, that the uniform distribution is defined by this upper and lower bound. So that's very much the case that we will be using a lot of definite integrals in this example. Okay. Well, in fact, we do in almost every example, but it's sort of more crucial in this case because they're well defined. So in this case, g of x is x over cubed, and we have f of x equals 1 over 6. So this is our definite integral here. The expected value of x cubed is the integral from 2 to 8 of x cubed divided by 1 over 6. Okay, and we can move the constant term outside the integral, and essentially what we're dealing with there is the integral of x cubed dx. Overall, we have the expected value of x cubed equals 1 over 6 times the integral from 2 to 8 of x cubed dx. But essentially, we'll just look at the x cubed part first off, and that is, when we integrate that, we have a definite integral that evaluates as x to the power 4 divided by 4 divided on the interval from 2 to 8. So essentially we evaluate our integral at 8, evaluate it at 2, and subtract the difference, or find the difference. So 8 to the power of 4 divided by 4 minus 2 to the power of 4 divided by 4. That is 4096 divided by 4 minus 16 divided by 4, which is 1024 minus 4, which is 1020. Okay, so evaluating the expected value, recalling the constant term. Okay, so the expected value of x cubed is 1 over 6 times 1020, which is 170. So therefore, the expected volume of the cube is 170. Okay, we'll leave it there.